Okay, so I'm going to record, and so that as we go through this, if you have questions, I'll answer them, and then if anybody missed this, they can actually catch up on what we have here. The first part of this I'd like to do is administration. If nobody has any questions right now, I can start with that. So as you may have seen, all chapter 12 and 13 videos are uploaded now, and chapter 12 and 13 homework are due Friday. Okay, we're also going to have the quiz come out on Friday as well. And that'll be focused on chapters 12 and 13. This week, I will have chapters 14, 15, and 16. Those are our last three chapters that we'll have. We're going to upload those this week and over the weekend. And then those homeworks will be due in a little bit later. Excuse me. Those homeworks will be due respectively, let's see, 14 and 15 will be due next Friday on April 29th. The following one will be due on Sunday, May 3rd. I didn't want to have three homeworks due all at once. I wanted to spread them out a little bit. But chapter 16, which is polymer chemistry, is our last chapter. After that, we'll go ahead and have a little bit of time for review. So the office hours on that week will focus on the review, and we'll talk about the final and the format of the final, etc. Okay. So let's see what else we have here. So chapter 12 was aldehydes and ketones. Chapter 13 was introduction to carboxylic aldehydes. With our next chapter 14 is carboxylic acid derivatives. And then we'll have 15, which is enolate ions, which is a derivative of the aldehydes and ketones. And then 16 is going to be polymer chemistry, which is actually my specialty. So I get really excited about polymer chemistry, but we'll get into that as well. Are there any questions specifically about chapters 12 or 13? Aldehydes and ketones and their reactions, or carboxylic acids and their introduction to carboxylic acids. Okay, well, go ahead and use the chat if you want to. I will also, so what I want to do is I want to kind of hit the highlights about aldehydes and ketones. I think there's some, the most interesting parts of aldehydes and ketones have everything to do with what to look for if you're not really sure what's going to happen because of the structure of the aldehyde or ketone. So the whole point of this section here is the idea of the carbonyl group. We're actually going to be using reactivity of the carbonyl group and using reactivity next to the carbonyl group for the next 4 chapters in particular. Enolate ions are specifically one over from that. Carboxylic acid derivatives are all about having a carbonyl with some other electronegative atom on there. And aldehydes and ketones are the carbonyl with a hydrogen or carbon bonded to it directly. So that being said, the idea that the carbonyl is actually a double bonded pi bond. It's a pi bond, but it's a polar pi bond. Unlike the pi bond we get when we have just a carbon-carbon right here, because that's a non-polar bond, we actually have a polar pi bond. Okay, so this is our 2p orbital overlapping with our 2p orbital, but remember that the oxygen is more electronegative, so it's pulling electron density toward it. Even though we have that double bond, we have a single bond being pulled as well as the double bond, giving us the carbon having that uniquely partially positive structure. Okay, that's where all the reactivity lies in our aldehydes and ketones, and that's where our reactivity lies in our carboxylic acids as well. Okay, so we can do a couple different things once we have this aldehyde or ketone. I'm not going to go through nomenclature. A lot of the things we can do is the fact that it has this polar bond, we can do dipole-dipole interactions, meaning that we can use it to dissolve things, okay? So that's one of the interesting properties of the aldehydes and ketones. But as such, it doesn't hydrogen bond specifically by itself. And carboxylic acids do hydrogen bond, but the aldehydes and ketones don't, Okay, moving on to the other interesting reactions here. So the first thing we can do is we can actually do a nucleophilic addition to the reaction. What that means is that we have something that has a negative charge or a lone pair, and it's going to attack the carbon because it has the partially positive side, okay? And if you don't have a good leaving group, in the case of having a hydrogen or a carbon here, then it just adds to the system. If you had a good leaving group, and we'll see this in carboxylic acids, that you can actually get substitution on that carbonyl. But when we're talking about aldehydes and ketones, we tend to do additions across them because of this having a lack of good leaving groups, okay? So our first addition reaction that we're looking at here is the addition of a Grignard reagent, which is basically using a weak polarized carbon magnesium bond to basically give us the concept that we have this carbon anion. It's bonded to the magnesium, so it's kind of stabilized, but it still reacts as that carbon anion. And so therefore it does the addition reaction across the aldehydes and ketones. The key here that in a Grignard reaction is that if you have formaldehyde, where you have 2 hydrogens on your carbonyl here, that's the simplest aldehyde we have, you always get a primary alcohol. If you have a regular aldehyde, when it has a carbon and a hydrogen on it, you always get a secondary aldehyde. And if you have a ketone, you always get a tertiary alcohol. I'm sorry, I meant alcohol in the second slide. So we can actually design our system that if you can use the same Grignard reactant, you can make a primary, a secondary, or a tertiary alcohol by choosing your aldehyde and ketone carefully. Formaldehyde, primary, regular aldehyde, secondary, and a ketone will always give you tertiary. Oh, I'm not sharing. All right, I'm gonna have to start again. All right, thank you. I'm not sharing. All right, let's go grab, there it is, share screen. Share. All right, do we see our screen now? Chat. All right, good. Sorry about that. You can chime in, it's okay. All right. So let's see. I'm gonna go back and show a couple of slides over here. All right, so what I was talking about was that the fact that the key part of an aldehyde or a ketone or even a carboxylic acid is the carbonyl functionality. And the reason the carbonyl functionality is so important for its reactivity is the fact that we end up with a carbon oxygen double bond, and we have a sigma bond here between the carbon and the oxygen, and then we have this p orbital pi bond. That pi bond and that oxygen here is a polar pi bond, not a carbon-carbon bond. Double bond is not polar, and therefore it reacts differently. Either side can react, and they react in a more similar fashion. In the case of the carbonyl, we have a very polar bond here, which lends it to having that reactivity of having the resonance structure look something like this, where we actually see it as one of the contributing resonance structures is our regular bond here, plus having a positive side here. That polarity of this double bond here is where all the reactivity on this group happens. And so we can see that as well. Okay, so in the reactions we can do, the first thing we want to think about is the idea that we can have a nucleophile or have something with a negative charge or even a lone pair come in and attack the carbon and do an addition on that, because we go back to this sp3 hydrides. The reason we tend to do additions on aldehydes and ketones is because the R groups here would be hydrogen or carbon, and they would have to leave as a hydrogen anion or carbon anion, which are very poor leaving groups. That's why when we have aldehydes and ketones, most of the time we're doing addition reactions. When we move to carboxylic acids, you'll see we can actually have better leaving groups, okay? So in the carbonyl compounds we're starting with, we're having an addition by a nucleophile. And the first nucleophile we get to play with here is the Grignard reaction. And in the Grignard reaction, we have the idea that the magnesium carbon bond is a very polar bond, okay? So if we looked at its resonance structure, the carbon's gonna carry most of the negative charge, the magnesium is gonna carry most of the positive charge, and therefore the carbon acts like a nucleophile and attacks the positive side of the carbonyl, okay? That being said, we can use this to our advantage to create different things, okay? So when we have something where we have formaldehyde, our simplest aldehyde, which has 2 hydrogens on that carbonyl, when the Grignard attacks it, we always form a primary alcohol, okay? Because there's already 2 hydrogens on our formaldehyde, we end up with our primary alcohol here. Whenever we have a regular aldehyde, which is a hydrogen and a carbon bonded to the carbonyl, we always get the secondary alcohol. And whenever we have a ketone, because we already have 2 R groups on there and neither one's going to leave, we always get a tertiary alcohol. So the ketone or the carbonyl functionality has a positive charge. The Grignard has a negative charge and adds to it, giving us a primary, secondary, or tertiary alcohol. Okay. So in the third set of slides, we move on to what we call acetals. And so the first is what we call a hemiacetal or a half. And the reason it's half is that we have 1 equivalent of water plus 1 equivalent of an alcohol on here. And so that's the hemiacetal. And this is moving back and forth in a very rapid fashion, back and forth between the ketone and the hemiacetal. And they're not as specifically useful as the acetals. The acetal is when you have 2 alcohol functionalities, you've lost water. These tend to be a little more stable and have an interesting feature is, notice we've removed the carbonyl carbon. We do not have a double bond on that carbon anymore, meaning it's no longer attacked by nucleophiles, okay? So the most useful acetal we have is what we call is the cyclic acetals right here. These are the most synthetically useful because they are very stable to a lot of things. Now, when we take this carbonyl away and create this acetal out of it, this cyclic acetal, we have taken that partially positive carbonyl, carbon, and turned it into an ether. Ethers are very stable and therefore don't react very often. And that way we can use other reagents that would normally have reacted with that partially positive carbon, partially negative oxygen of the carbonyl, and we've taken out that polarity, we've taken out that reactivity. So we sometimes call it a protecting group. It's protecting the carbonyl while it's there, and then you can regenerate it just by adding acid at the end. Oops. So that's why we call it a protecting group here. We can selectively react one or the other aldehyde to make it so that in the end of the reaction, when we add acid, we regenerate that carbonyl compound. So in the case here, we actually did it where we took this aldehyde, turned it into an acetal, one of these cyclic acetals, then did additional reactions on another aldehyde where it is consumed. Notice this is a regular aldehyde, so it forms a secondary alcohol. But by adding our acid in the end, we regenerated our original aldehyde. So we're actually using it as a way to hide our carbonyl, take it away from being reacted with nucleophiles by protecting it as an ether. And that's how the whole acetal system works. And so we're basically taking away its reactivity by turning it into that ether. Now, we're doing the same thing when we turn it into an amine. We're basically using nitrogen to protect it. Remember, nitrogen is not as electronegative as oxygen, and therefore it's a less polar bond, making it less susceptible to reactions with nucleophiles. That's why we would do that reaction here. Okay, so the last key thing about the aldehydes and the ketones is that we have an enol-keto-tautomerism, okay? And the key here is that while we do not form very much of this form at all, this is the less stable form, the enol form is the less stable form, it reacts differently than the keto form, okay? So the ketone, you know, it's stable to oxidation, it's stable to this, it's stable to addition, to substitution reactions, but the enol form, because it's got an alkene, can start reacting like an alkene and then regenerate the carbonyl. So that's where the enol-keto-tautomerism is the functionality. That's why we have different reactions that we can do on this. And the most notable of these reactions is we get substitution next to the carbonyl, okay? So we get substitution next to the carbonyl. We're not attacking the carbonyl itself. We are substituting next to the carbonyl. And that only happens because we can form that enol form. Having that double bond, it reacts and then regenerate the ketone form, okay? So that's the key step in this reaction. And again, you don't have to form very much of it, but when you do form it, it does react irreversibly. And then so you can have a tenth of a percent in that reaction, and it'll continuously react to form to get to the product eventually. Okay, so the other key fact about the enol is that because you're going through this sp2 hybridized carbon, you end up losing all your stereochemistry. If you started with stereochemistry, you are losing your stereochemistry. If the carbon next to the carbonyl had an R or an S specifically, it will lose it, okay? It's only the one right next to the carbonyl though. If you have a stereocenter that's more than one carbon away from that carbonyl, it's not involved in the reaction. We're not worried about that. So we only have to worry about the carbon that is right next to the ketone here. All right. So I know I'm running through this fast, so I'm just trying to hit the highlights of what I think is really important to think about. Once you figure that out, I think you'll see that that is, that kind of drives the reactivity, and that kind of drives where you have it. Okay, so let's talk about other things you can do. So if you have a ketone, ketones are very stable to oxidation because it's already oxidized down, except for one specific reaction. I'll talk about that. But the aldehydes, because you have a carbon-hydrogen bond here, you can oxidize that further, and typically you convert that to a carboxylic acid, which of course we learn more in chapter 13. Okay, so we can use a variety of different oxidizing agents, even air. These tend to oxidize slowly in air just by the nature that that's the most reactive bond in the system. This is the one time I think a ketone will react to give us another product. It's actually not the ketone being oxidized, it's the enol form being oxidized. So you're protonating the ketone, getting to the enol form, and that enol is acting like an alkene, and that alkene can be oxidized, okay? So most ketones do not do this, but every once in a while you'll find one that forms a nice stable intermediate that will do this. Okay, so another way to oxidize down aldehydes is to use what we call the Tollens reagent. This is basically silver is going from silver +1 to silver 0, transferring electrons to oxidize the carbonyl carbon down to the carboxylic acid. Okay, so because we have a carbon-oxygen double bond, we can reduce it. We can add hydrogen across that line, just like we can with alkenes. And when we do, we get different things. Aldehydes will produce primary alcohols. Ketones will produce secondary alcohols. Remember, if you want to produce a tertiary alcohol, you take a ketone and hit it with a Grignard reagent. So Starting with your aldehyde or ketone, you can get to primary, secondary, or tertiary alcohols by choosing your reagents. Okay, so again, in both of these reactions, we're adding hydrogen across the carbon-oxygen double bond. Okay, so we can do that just like we do with the double bond. We can add catalytic hydrogenation. It would be hydrogen plus a catalyst, and it'll reduce that down, but it'll also reduce down alkenes. So if you don't care if you're reducing down, you just go ahead and do the catalytic hydrogenation you'd normally do with an alkene. However, if you want to do it specifically, you need to use one of these metal hydride reagents, sodium borohydride or lithium and aluminum hydride. The key factor is that you have a negative hydrogen, a hydrogen with 2 electrons on it. And that's going to be the part that adds to the carbon that's partially positive. Okay, so the first step is typically the addition of that hydrogen to the carbonyl hydrogen, and then a complex with the boron and the oxygen of the carbonyl. And then when you add acid or water, it removes that boron complex, generating your alcohol. So again, our hydrogen, our hydride, is the part that adds across the carbonyl. It's the part that bonds to the carbonyl carbon, and then we regenerate the alcohol by acid hydrolysis. Notice that sodium borohydride does not react with alkenes. Okay, so catalytic hydrogenation will do both carbonyls and alkenes. Sodium borohydride will only do carbonyls, and so we can do selective chemistry on that based on what we have. Okay, so that's the highlights of aldehydes and ketones. And again, the whole concept is, think of that carbonyl carbon as partially positive, and that if you have something that's negative, it's going to react with that carbon. You can have protonation of the alcohol of the carbonyl oxygen to give us an enol keto tautomerization. And that protonation also gives us hemiacetals and acetals. And acetals take away the partially positive nature of that carbon, making it not susceptible to attack by nucleophiles. That's why we use acetals to protect carbonyls, and how we actually form them is by that protonation step. Okay. So I want to do a couple things with the regular carboxylic acids if we have time and no other questions, which we do. Okay, so carbonyl is just an extension. I mean, the carboxylic acid is an extension of the carbonyl. All we've done is, instead of having a carbon or a hydrogen on it, we've now added an electronegative element. And that one is oxygen in this case. And so the oxygen is in the carboxylic acid bonded to a hydrogen. Okay, so this gives us lots of chemistry. Okay, so the first thing we're going to see is that it gives us hydrogen bonding. Okay. Come on, hydrogen bonding. There we go. Gives us hydrogen bonding. And in most cases, we think of 5-membered rings or 5- and 6-membered being very stable. However, because the fact that we can have these 2 carboxylic acids with 4 atoms in each of these rings, it actually makes an 8-membered ring, but they kind of fit together like this, so that they're hydrogen bonding on multiple places at a time. And that stability, that hydrogen bonding those 2 carboxylic acids together, really changes its properties. It makes it more water soluble than before. It makes it higher boiling than before. It makes it higher melting than before. And it has everything to do with that, forming this kind of weird 8-centered complex. There's 8 atoms in this ring, and it's forming that, but it's bonding a couple times to each side. So that's why we have those solubility and the melting point properties associated with it. Again, if you have questions, go ahead and chime in. The chat's on, but I'm just also hitting the highlights. And if you have questions when I hit the highlights, go ahead. Okay. So like the name suggests, they are acids, carboxylic acid. They are the strongest of the organic acids, but they are weak acids in comparison with HCl and HBr and other things. So our pKa is above 0. So anything below 0 is a strong acid. So they are fairly good acids as far as an organic material goes, okay? That acidity does change with how close you are to an electron withdrawing group. Okay, let me stop mirroring. Uh-oh, here, I'm frozen. Let me stop sharing and reshare real quick. My iPad in its infinite wisdom decides to switch oh, I bet it switched networks on me. Yeah, it did. Let me change it real quick. Come on. Technology is great until it's not. Let me try one more time here. Come on, we're all on the same network. There we go. Yay. All right. So carboxylic acids are weak acids, but they're the strongest of the organic acids. And by adding electron withdrawing groups, you can make it more and more acidic. The reason that works is that you are taking more and more electron density away from this carbonyl group, and therefore it can stabilize more and more negative charge. Okay. However, it works best when that electronegative atom is right next to the carbonyl. Once you get further away, it diminishes the effect very rapidly. So things that are bonded right next to it are stronger than the things that are bonded further away. Okay. So that being said, carboxylic acids can react with base. In fact, the carboxylic acid can be deprotonated with sodium hydroxide where alcohols can't. And that actually lends us to a little bit of separation. The other things they do is they react with amines and ammonia to form very water-soluble salts. This happens a lot in things like benzocaine and other common pharmaceuticals we use. A lot of them have these ammonium salts made on them because they makes them so much more water-soluble. Okay. And the last thing about carboxylic acids that we want to talk about is that because it has that extra oxygen on there, it's really resist being reduced down to alcohols, okay? So it's very hard to do it with catalytic hydrogenation, if at all. You tend to not work with it, so you can reduce down an aldehyde or a ketone in the presence of carboxylic acid. You have to go very, very strong. You have to go lithium aluminum hydride to get it to reduce down, okay? So sodium borohydride will do other carboxylic acid groups, but carboxylic acids won't. So you can reduce down an aldehyde or ketone using sodium borohydride in the presence of a carboxylic acid. But if you have a carboxylic acid, you're going to need to use lithium aluminum hydride, and it'll always reduce it down to a primary alcohol. Okay? So you can do selectivity. One of the other things it can do is it can take that OH off there and replace it with an alcohol to liberate water and generate an ester. So the ester functionality is you don't have an OH on there anymore, you have an O with some kind of R group on there, and that's the general thing. We tend to drive this reaction to completion by removing the water or having a whole bunch of the alcohol around, so that the water can still go reversibly back, it can still act as a nucleophile, but when you have so much more of the alcohol around, there's more alcohol to generate the ester. And so either you drive it with a whole bunch of extra alcohol or you remove the water as you do it. Again, by adding water back to it with a little bit of acid catalyst, we can convert it back. So what we did in the lab was we added a whole bunch of extra alcohol to the system with just 5 drops of sulfuric acid, and that drove it to the majority product. I think our yields were probably in the 70 to 75%. We could have driven it further if we had had a distillation apparatus where we were removing water. Okay, so that works by that group there. So we're going to continue on with the different functional groups in our chapter 14, specifically looking at the acid halides. I said before, a carboxylic acid is our introduction to with an electronegative atom of oxygen. Well, we can have a derivative of that called the acid chloride, where we use an electronegative atom instead of oxygen. We're using a halide. And the most common is the chlorine because it's the most stable bond. So we took up these acid chlorides, but we can use any halogen atom, but chloride's the one that is the most stable and most useful. And the last thing I think is key in carboxylic acids is the fact that, okay, we have CO2 with a hydrogen on the end of it. Therefore, we can lose CO2. But this works best when we have a carbonyl 2 carbons over, or the beta carbon. And the whole key for that beta carbon is the idea that you can form this cyclic intermediate right here. We can transfer the proton from the carboxylic acid to the ketone or aldehyde, which then can kick all the electrons in, liberating CO2, which goes away as a gas. And then we have a tautomerization of our enol form back to our ketone. And so that's the driving force for this decarbonylation. But that's why it makes it easier to decarbonylate a beta ketone compound or a beta aldehyde compound, because of this formation of this 6-membered ring. Okay, so look forward to the chapter 14 carboxylic acid derivatives chapter. I'm recording that today. You should see it up today or tomorrow. So any questions? I have a couple more people. I was going to go ahead and do some administration as well. While you're typing your questions into chat, I'll talk about that. Chapter 12 and 13 videos are up on the website. Go ahead and watch those. Chapter 12 and 13 homeworks are due on Friday. They're due on Friday. I'm trying to get it so that we're all caught up. We had 2 weeks of this. For the quiz, we're going to have the Dropbox quiz again on Friday. Chapters 14, 15, and 16 will appear on the website this week. However, the homework for chapter 14 and 15 will be due next Friday, and then the homework for chapter 16 will actually be due on Sunday. Chapter 16 is polymer chemistry, and so I didn't want to have 3 homeworks in the same week, so I pushed it back several days to give it to us on Sunday. And what that'll give us is some opportunity to finish up those last 3 chapters and do any kind of review we need to do for our exam on the beginning of May. So I'll have a review set up for that, and I will have a final answer on how we're going to administer the final as well. Okay. So that's all administration. I will have office hours on Friday, unless I'm sick again. Sorry, I threw my back out and I couldn't have office hours, but I'm better now. Yes, the final is cumulative. It'll be chapters 1 through 16. It's going to be multiple choice. I'm hoping to administer it through sapling as a multiple choice test. The details, I'm still working with the faculty up at Texas State. We're trying to come up with the best way to do my other 2 organic classes, and I'm going to do your class like theirs. Looks like we're going to administer it through sapling, and it'll be administered on the day our final is supposed to be in the regular semester. So if I can look at that real quick. So our final should be on May 8th. So I'll have that up and running by May 8th. And so, oh, also, I spent the whole weekend when I wasn't on painkillers getting all of our assignments, all of our grading up to date. So please check tracks to make sure your grading is up to date. If you had issues with sapling, I think I emailed most of you individually. So I think all of the grades look accurate to me. Please double check those to be sure. I did have a few issues with grades that may or may not be correct in the take-home test. So just double check the take-home quiz. If you turned it in, you should have a grade. If you didn't turn it in, you shouldn't have a grade. But I think everything should be up to date through chapter 11 homework and through our last quiz. So go ahead and double check that if you can, please. So let's see, I'm looking at it now. Doesn't like it. So yeah, up through quiz 8 should be posted. If you don't have a grade there, go ahead and email me. We'll see if we can find it. All of your, most of your homework grades, all your homework grades should be in there up through chapter 11. So if you have questions about that, go ahead and email me, but double check for me, please. It looks like overall, we have almost everybody still participating, so that's great. We only have 5 homework assignments left, so let's keep doing that and keep doing great at that. The midterm, the exam 2 grades should be in. If you don't have an exam 2 grade, go ahead and email me and talk to me about that. And so our last grades are our final grade and chapters 12 through 16 homework. And I think we're having 2 more quizzes. So overall, we're going to accomplish what our original syllabus was set out to do. And I think that overall, as a class, you're doing great, and we're, adapting quite well, I think, to this new environment. Okay. Other questions? All right. Lab. Our last lab will be posted today. And again, just like last time, you'll be able to upload the data sheet and post lab, and you'll have an unknown associated with your name. All of that, the video will go out today, the unknowns will go out on Thursday. And so all you have to do is fill in your data sheet for your unknown, and I will give you what that should look like as a takeaway sheet. But I believe a lot of the grades have been posted. Not everything has been graded up to now. I'm trying to get all the grades up to date for the lab as well. So let's see where we are. Yeah, it looks like a lot of the lab reports are posted, but not all of them. So chapter 6, lab report 6, 7, and 8. 8 is the carbohydrates lab. Chapters 6 and 7 are the ester and the other labs. So I'll try to get as many of those updated as possible. The lab be due the lab is due on Monday. So it's released, and then the unknowns are released on Thursday, and you have Friday, Saturday, and Sunday to complete it. Labs are due on Monday at 5 p.m. And I thought I posted that in the email as well. So when I send out the lab unknowns, I typically have the, let's see, lab unknown codes. Okay. So I will send out a due time on the lab unknown codes, and I will also send it out on there. Let's see. I believe I'll send it out as one. Let's let's see. I did send it out, but it sent out a lot earlier. So, okay, I'll make sure to send out the unknown codes with the due date of Monday at 5 p.m. With it all in one email, so it'll be easier to look at. Okay. Does anybody have any questions specifically about aldehydes, ketones, or carboxylic acids? Okay. Our last lab is carbohydrates. You're going to have to pause the video a lot to write down which reagent is which to get that down. It's the video itself is fairly short, but you have to pause and make observations and pause and make observations. But I believe we've annotated it so that after you see the image, there is what the different carbohydrates are so that you can make a chart out of it. Excuse me. I was getting better until it rained. Okay. So we ended up with 6 or so of us. I think I've communicated by email or by video conferencing with almost everybody. Everybody seems to be still moving along, and that's great. We should be sending out an electronic evaluation for this class because I can't do an in-class evaluation. So I should be getting all the information about that sometime this week or next week, and we'll do it before the final. And so you'll have some opportunity to give some feedback. Obviously, this has been an unusual year. So I hope we've been able to adapt appropriately such that we can all keep striving forward. Let's see what this email is about. Oh, Honor College. Okay. Not bad. All right. So how's everybody holding up? Okay, good, good. So yeah, we had to update we had to get a faster internet at our house, so we're paying more for internet now. But my kids are both online classes. They're both, one's in junior high, one's in high school. My wife, of course, teaches at university, so she's online all the time too. And so between the 4 of us, we've taken out 4 corners of the house, and we're just sitting down and Wi-Fiing all the time. I'm lucky enough to have an office where I can shut myself off from everybody else. Okay, good, good. I'm glad everybody's finding a way to persevere. My daughter did a project on Charles Darwin a couple years ago, and her friends were like, "Oh, survival of the fittest, survival." No, no, no. My daughter said that no, that's not what he said. He said that it is all about the ability or the desire to adapt. So if you have the ability and desire to adapt, you are more likely to move forward on your, let me stop sharing here. Okay. So it's all about, we have to adapt, we're going to adapt, let's adapt and move forward. So just so you can learn something from everyone. Okay. Well, what I'm going to do now is, now that the majority of this is done, I'm going to stop recording and then I'm going to go ahead and upload that. So if you had any questions about what the highlights for those chapters are, you can see them. And if you wanted to hang around and ask individual questions, that you can do it as well. So I'm going to stop recording now.